Hello dear students, this is your physics teacher Ashish Sharma, and this is the second video in continuation with the first video already uploaded on thermodynamics. In this video we will discuss the second half of chapter thermodynamics for class 11th, and we will finish the syllabus of 2020-21 session of thermodynamics unit in this syllabus. So we have discussed in earlier lecture thermal equilibrium, zeroth law of thermodynamics, definition of temperature, heat, internal energy and work, and also we discussed how to calculate work done in expansion of isothermal change. The second important change is adiabatic change or adiabatic expansion. In this lecture we will start with this topic, work done in an adiabatic expansion. As we know from isothermal process, formula of work done when a gas changes its pressure, when a gas at some pressure changes its volume from V1 to V2, we can always integrate the pressure in order to find out the work done as it is mentioned in this equation. Also, the condition for adiabatic change which we have discussed in previous video, that PV raised to power gamma remains constant. We can also write this equation in other two forms. So we can say that PV raised to power gamma is equal to K. From this equation the value of P is KV raised to power minus gamma. When V will come on right hand side, the sign of power will change. Putting this value of pressure from equation 2 to equation 1, work done is integration V1 to V2 K V raised to power minus gamma dV. K is a constant, can be kept outside the integral sign, and the integration of V raised to power 1 minus V raised to power minus gamma is V raised to power 1 minus gamma divided by 1 minus gamma. Lower limit, upper limit. Putting the limits, upper limit minus lower limit, formula of work done is equal to K divided by 1 minus gamma, V2 1 minus gamma minus V1 1 minus gamma. We can take K inside the relation and inside the bracket, and we can write it like KV2 1 minus gamma minus KV1 1 minus gamma divided by 1 minus gamma. Now here is the tricky part. As we know that PV raised to power gamma is constant, so in place of first K I can put before that let me tell you, this K can be used as P1 V1 raised to power gamma as well as P2 V2 raised to power gamma. So at place of this first K I will write P2 V2 gamma, and at this second place I will write the value P1 V1 gamma for K. Putting these values in this equation will get the result, because when you will put K P2 V2 gamma, so V2 gamma multiply by V2 1 minus gamma, base is same, power will add and it will give you P2 V2. Similarly, when you will put K at this place, P1 V1 gamma, V1 gamma into V1 1 minus gamma will result in V1, plus gamma and minus gamma will cancel. So desired relation for work done is P2 V2 minus P1 V1 divided by 1 minus gamma. Also we know that for 1 mole of gas, P2 V2 can be written as RT2 or P1 V1 can be written as RT1. Placing these values in above equation will get and taking R common, R divided by 1 minus gamma T2 minus T1, which is the second relation for same work done in adiabatic change. Moving ahead, there, as you if you remember that I told you four cases or four changes which were isothermal, adiabatic, isochoric and isobaric. Out of these four changes, we have discussed the work done of isothermal and adiabatic. Up to this point, work done of adiabatic is discussed. In isochoric process, the meaning of isochoric is constant volume, so dV is equal to 0. If dV is equal to 0, W also becomes 0. And in isobaric process, when your volume is constant, work done is represented as pressure multiplied by change in volume, because in isobaric your pressure remains constant. So work done is pressure into change in volume, or writing PV2 as mu R2 and PV1, because you can write it like PV2 minus PV1, and PV1 writing PV1 as mu RT1. This work is also equal to taking mu R common, mu R T2 minus T1. The next topic is first law of thermodynamics. First law of thermodynamics is quite simple. Whenever heat is added to a system, it transfers to an equal amount of energy in some other form. Or in other forms, we can say that first law of thermodynamics is just the energy conservation, that energy transferred to a system must convert from one form or another. It can neither be created nor be destroyed. The equation is very simple. dq is equal to du plus dw. If dq is the heat supplied to system, either it must change the internal energy of system, or it should spend in some work dw done by the system. So you can also consider dq as pocket money given to you, and then if we consider du is the portion which you save, then du is the change in your saving, and the remaining portion if you spend, then dw is the money spent by you. It is that simple. We can apply the equation of first law of thermodynamics to various cases or various processes in thermodynamics. Okay. In isothermal process, as we know, change in internal energy is zero because temperature remains same. So the internal energy, so the dq is equal to du plus dw becomes dq is equal to dw, because the complete equation is dq is equal to du plus dw. As your du is 0, dq becomes equal to dw. In adiabatic process, there is no exchange of heat, hence dq becomes 0, and our first law of thermodynamics becomes du plus dw is equal to 0, or we can say du is equal to minus dw. In isochoric process, as there is no change in volume, volume is constant, so work done is 0, because as w is defined as dw is defined as pdv. So if volume is constant, dv is 0 and dw is 0, so dq becomes equal to du. In cyclic process, when system comes at same state, always its internal energy becomes same, so du is equal to 0 and dq is the dw. Heat supplied to system is always equal to work done by the system. For melting process, we are having dq is equal to ml, where m is the mass of the substance and L is the latent heat which is required to change the physical form. And if these things happen having without change in volume, dw becomes 0. Thus du becomes equal to dq or ml. So that is how first law is applied on melting process. Or in other words, you can say increase in internal energy is equal to heat supplied to increase in internal energy du is equal to heat supplied to the system dq, which in turn is equal to ml, which utilized in changing the state, and temperature remains constant. Boiling process, all the internal energy which is change, like if no boiling will happen, then ml is equal to du is simply state change, but because due to boiling the volume of the vapors of liquid increases, so work done in that expansion is pv2 minus v1. That energy is being utilized from the energy supplied ml, so your du becomes ml minus p v2 minus v1. In other words, you can say du is equal to dq minus dw, or dq is equal to du plus dw, which is nothing but the first law of thermodynamics. Moving on to next topic, if you remember that I used this Mayer formula in ninth unit kinetic theory of gases, and I told you that you must have you must have gone through Mayer's formula in thermodynamics. So here I am in thermodynamics with Mayer's formula. It is the relation between principal specific heats of a gas, that is Cp and Cv, which are the specific heat of gases at constant pressure and constant volume, and Mayer formula is Cp minus Cv is equal to R. We used this formula in the video lectures of kinetic theory of gases for calculating gamma. First, let us consider a gas at constant volume. For this, change in heat supplied dq is equal to Cv dt. As the volume is constant, so no work is being done by gas. So my du is equal to dq, and as I calculated dq is Cv dt, so du is equal to Cv dt. That is first equation, remember this. Now for constant pressure, now work done is not zero, and let us take dq dash is the amount of heat supplied at constant pressure to a gas, and change in temperature is dt. So dq dash is equal to Cp dt, where Cp is the specific heat at constant pressure, and dw dash is the work done by the gas, which is pdv. So if I'll put them in first law of thermodynamics, dq dash is equal to du dash plus dw dash. Dash is indicating that I am doing it for constant pressure. Putting the values, Cp dt is equal to du dash plus pdv, or du dash is equal to Cp dt minus pdv. Now as both the gases are having same change in temperature, same rise in temperature, their change in du must be same. Their change in internal energy must be same. So du must be equal to du dash. Comparing equation 1 and 2, Cv dt is equal to Cp dt minus pdv. So Cp dt minus pdv is equal to Cv dt. Taking dt common, Cp minus Cv, and we can write pdv on right hand side and Cv dt on left hand side. So and one more thing, as your pv is equal to RT for one mole of gas, so differentiating pdv is equal to R dt for 1 mole of gas. So I can write R dt at place of pdv. dt से dt cancel हो जाएगा, and Cp minus Cv is equal to R, which is desired relation or Mayer formula. After this, we are having next second law of thermodynamics. Second law of thermodynamics is quite interesting. It tells us how heat energy spontaneously flows from high temperature to low temperature and cannot flow by its own from low temperature to high temperature. And there are many ways of saying this, like entropy of universe is continuously increasing, or according to the second law of thermodynamics, heat flows spontaneously from a substance at higher temperature to a substance at lower temperature. Heat does not flow spontaneously in reverse direction. There are other scientists who also gave different definitions. Like according to Calvin Planck's statement, it is impossible to construct a heat engine which would absorb heat from a reservoir and convert 100% of heat absorbed into work. According to Clausius' statement, it is impossible to design a self-actuating machine unaided by any external agency which would transfer heat from a body at lower temperature to another body at higher temperature. If you will consider the example of AC in your house, then during summers temperature at the rooftop is higher than temperature in the room, and still your AC is rejecting or transferring heat from your cold room to hot ambience. As heat is traveling from lower temperature to higher temperature from your room to the rooftop, work is being done by the machinery of AC, that is compressor, and a huge amount of energy is being consumed by AC. So that is what second law of thermodynamics is saying, that heat can flow by itself from high temperature to low temperature, but heat cannot move by itself from low temperature to high temperature without help of any external agency. Otherwise, uh, an AC would be able to work without consumption of electricity, which is not true. And the last topic in the syllabus is reversible and irreversible process. And you can see, if you will check in the book, that Carnot theorem and Carnot engine and heat pump, etc., these topics are not in syllabus for your 2021 syllabus. Otherwise they were in syllabus of thermodynamics earlier. It is reduced. And the last topic is reversible and irreversible processes. So for a process to be reversible means when a process will come back to the same stage, any stage from where it was earlier in past history, without having any other change in universe, is known as reversible process. There are few conditions for a process to be reversible, and that is, the process should be proceed at an extremely slow rate. The reason for proceeding at extremely slow rate is that so that system and ambience will get enough time to exchange heat, so that system may remain in thermal equilibrium with the environment. And not only in thermal equilibrium, it must remain in all three types of equilibrium from the ambience, like mechanical equilibrium must be there and chemical equilibrium must be there. The second point is, the system should be free from dissipative forces like friction and viscosity, because energy spent in these forces cannot be recovered back. In fact, reversibility is an idealized concept which can never be attained in real life. It can at best be approximated only. Some examples of approximately reversible processes are: an ideal gas allowed to expand slowly and then compressed slowly in a cylinder fitted with a frictionless movable piston and with conducting walls, so that it can exchange the heat from the surroundings. And electrolysis can be taken as reversible process provided resistance offered by electrolyte is zero, and because energy spent in resistance of electrolyte can never be recollected, I square RT, Joule's law fitting effect. And slow compression and expansion of a spring can also be treated as reversible process. So a process which does not satisfy even one of the conditions for reversible process is called an irreversible process. अगर कोई भी एक condition reversible में से पूरी नहीं होती है तो उसे हम irreversible process कहते हैं. In fact, all spontaneous processes of the nature are irreversible. For example, transfer of heat from hot body to cold body, ordinary expansion of gas, diffusion of gas, stopping of a moving body through friction are all examples of irreversible processes. Irreversibility arises mainly from two causes. Many processes like free expansion or an explosive chemical reaction take the system to non-equilibrium state, and most processes involve friction, viscosity, and other dissipative effects. And as the dissipative effects are present everywhere, they can be minimized only and cannot be fully eliminated or reduced to zero. Therefore, most processes we deal with are irreversible processes. Some additional examples of irreversible processes are production of heat on passing an electric current through a wire. The same amount of heat is produced in given time even when the direction of current is reversed. So it means ऐसा नहीं है कि हमने A to B किसी वायर में अगर हमने कंडक्ट करंट फ्लो किया तो हमारी हीट प्रोड्यूस हुई है H, और अगर अब हम B to A करंट फ्लो करवाएंगे तो वो हीट एब्जॉर्ब हो जाएगी कंडक्टर में, ऐसा नहीं होता. दिस हीट इज ऑलवेज रिलीज्ड इनटू द एटमॉस्फेयर. तो दैट इज व्हाई इट इज एन इरिवर्सिबल प्रोसेस. Most of the chemical changes or chemical reactions are irreversible because they involve change in the internal structure of constituents, the decay of organic matter, rusting of iron, sudden compression or expansion, or mixing of two different substances like water and alcohol, the formation of solution of a solid in water are examples of irreversible process. What is the importance or significance of the concept of irreversibility? It is that main concern of thermodynamics is the efficiency with which heat can be converted into mechanical work. The second law of thermodynamics ruled out the possibility of a perfect heat engine with 100% efficiency. तो जो सेकंड लॉ ऑफ थर्मोडायनेमिक्स है वो हमें यही बताता है कि हम 100% एफिशिएंसी का इंजन नहीं बना सकते, क्योंकि कुछ ना कुछ एनर्जी डिसिपेटिव फोर्सेस में ज़रूर स्पेंड होगी. इट टर्न आउट दैट द heat engine based on idealized reversible processes achieves the highest possible efficiency. All other engines involving irreversibility of some kind have much lower efficiency. Therefore, reversibility is an important concept in thermodynamics for designing of efficient machineries. But again, I will remind you that Carnot engine, heat refrigerator or heat pump, etc. are not in your current sessions syllabus. So with this, we are finished with all the topics of syllabus of thermodynamics. Okay, revise them properly, and if there is any doubt, then let me know in online classes. Okay, take care. Thanks for watching. Bye bye.